Hello students, in this class we will discuss about the speed of three-phase induction motor. Last class we discussed about the working of three-phase induction motor. In that working, once again we will recollect all those points. So generally the three-phase induction motor supply is given to the stator and stator will generate the flux. This is just assume that this is the rotor and this is the stator. It will take the three-phase AC supply. By using the three-phase AC supply, rotor will be connected to some shaft. Assume that we have some shaft. So rotor gets rotation. Rotor gets rotation. So in this we have involved some principles, and by using that principles, induction motor will rotate. But we have to understand the important concept, speed of three-phase induction motor. Speed of three-phase induction motor. So before understanding the speed of three-phase induction motor, first we will look at the parts, the speed of the parts of the three-phase induction motor. First, always stator speed. Stator is always constant, you know that. Stator speed always constant. That means stator speed is 0. And rotating magnetic field, we have two magnetic field. That means we have stator as well as rotor. Stator or rotor, both having the RMF. RMF means rotating magnetic field. That means flux will rotate. Flux will rotate is nothing but RMF. So always rotating magnetic field always rotates with synchronous speed. What is the synchronous speed? Synchronous speed can be defined by this formula, Ns equal to 120F by P. Ns synchronous speed, Ns is the synchronous speed. Synchronous speed means constant speed. This is a always constant speed. Here F is frequency, P number of poles. So by it will work on it, right? At any condition, the motor will be, the rotor will be standstill, and rotor will be some rotation, and rotor will be at synchronous speed. Any condition, field speed is always synchronous speed, and but rotor speed will be varies. Rotor speed will be varies. Okay. So rotor speed should be varied. Rotor speed is represents with NR. This is always constant. Stator is always constant. Stator at any condition, it doesn't rotate. We know all these 3 points. Now we will look into the 3 cases. So first case 1. Case 1. The case 1 represents rotor at starting condition. At starting condition. At starting the rotor magnetic field, rotor speed is at starting condition, rotor speed always 0. You know that starting doesn't rotate. After some time it will rotates. And we have third case 2. Rotor is rotating. Rotor rotates with the NR, but the NR is less than synchronous speed. NR is less than synchronous speed. At this condition, so at this first condition, very important condition is for case 1. For case 1, we will discuss about. For case 1, rotor speed is 0. So in order to produce the magnetic field, the most important case is relative speed. That relative speed is synchronous speed minus 0 ns. Then rotor will try to rotate. Rotation is possible. And what about for case 2? For case 2, relative speed is again ns less than nr. We get some value, so we will get some k. Then rotation is possible. It will also rotates. And we have case 3. In this case 3, look at the case 3. For example, the rotor rotates with the synchronous speed. At startingly 0 speed, and it will rotate with some nr speed, and after that it will reach the synchronous speed. Then what happened? The relative speed equal to ns minus rotor speed is also ns, then 0. There is no relative speed. Whenever relative speed is 0, then rotor comes into the standstill condition. That means rotor doesn't rotates. Standstill condition. So if you observe here, first rotor speed is 0. After that, the second case, rotor speed is rotates with some speed, we don't know some speed. Case 3, rotor rotates slowly, increases and reaches the synchronous speed. After that again rotor speed is 0, and again rotor speed is n, again rotor speed is ns, like that. So it will continue like this. So the rotor speed of 3-phase induction motor varies like this. What is the reason for varies? In order to vary this, the main reason is by the rotation, relative speed value changes. Relative speed value varied. So by change in relative speed, automatically the speed of the value also changes. So by relative speed varied, then automatically rotor speed also varies. This is a problem with the induction motor to understand the rotor speed. So in order to understand very clearly, so we are introducing a factor called slip. Slip is the factor. By using that factor, we will understand the speed of the induction motor. So now we will discuss the next topic is the slip. Slip represents with the S. So slip is defined is a ratio between difference of synchronous speed and rotor speed to synchronous speed. Understand? Slip is nothing but a ratio between the first thing is the difference between synchronous speed and rotor speed. So that is, so we can write slip is the factor, this is the ns minus nr to ns minus nr or n to the synchronous speed. This factor is introduced to understand the speed very clearly. Always slip represent in the percentage of slip, that's why we have to multiply with 100 here. We have to multiply the 100 here. Once again, what is the slip? Slip is the ratio, is ratio of difference between synchronous speed and rotor speed to synchronous speed. This is the slip. By using this slip factor, we can clearly understand the rotor speed. Rotor speed. Slip, if you observe here, ns minus nr. Here first we will look at what is ns. Ns is, name it as the, S represents the synchronous speed, S represents the synchronous speed. So this ns equal to 120 f by p is the formula. What is f here? F is the frequency of supply or frequency. What is p here? Number of poles. Number of poles of the machine. Number of poles of the machine. Yes. What is nr? nr, speed of the induction motor. This nr represents rotor speed of induction motor. Induction motor. Here slip value in between 1% to 3% in terms of percentage, or this value is always 0.01 to 0.03. Slip value is, in terms of percentage, it is 1% to 3% and 0.001 to 0.003. Okay. If you observe clearly, slip ns minus nr, generally here speed units are represented with rotation per minute. Rotation per minute. In shortcut we can call it as RPM. Rotation per minute, shortcut we can call it as RPM. So if you observe here, ns minus nr both are RPM and this is RPM. RPM cancel, there is no units. Slip, generally it is a constant, doesn't have any units. Constant R doesn't have any units. Right. It doesn't consist of any units. So by using this slip, we can define the rotor speed. So now we will write the synchronous induction motor speed. So now we will write the speed of induction motor. Direct formula is speed of, very important formula, speed of induction motor by using the slip. Rotor speed nr equal to ns minus 1 minus s. Understand, this is the speed of the speed of the induction motor. nr, speed of induction motor in RPM. ns, synchronous speed. Where is s is there, that is only synchronous speed. Don't confuse. Units are so RPM. S is the slip. You know how to find out the slip. Slip is simple formula, that is ns minus nr by ns. By using this we can find out the speed of induction motor. This is very important formula. This is very important formula. Now you understand? Yeah. Generally the speed of the induction motor varies like this. So at starting it is the 0, and after that it will reach some speed. So after that it will reach synchronous speed. After it will 0, it is synchronous speed. So to understand at a particular time it is very difficult. So why the problem is occurred in these motors? The problem is due to the relative speed. Relative speed is decides the synchronous speed. What is relative speed? Relative speed means the speed between flux and conductors. The speed between flux and conductors. Relative speed is nothing but, what is relative speed here? Relative speed is speed between flux and conductors. Flux and conductors, right? So that's why the speed will be varied. But in practical case, the speed will be varied in between points, not 0 and synchronous speed. Okay, and here, so in order to understand the speed, so we will find out a ratio. That ratio is slip. Slip is simply, it is the difference between synchronous speed to the rotor speed to synchronous speed into 100. Generally synchronous speed formula is 120 f by p. Here f is the frequency, p is the number of poles. Here nr is the speed of induction motor. Okay. Generally this s is slip always 1% to 3% if we consider in percentage values, or if you take in between the values 0.01 to 0.03 practically. S is a constant, it doesn't have any units. And speed of the induction motor, now we will discuss the speed of the induction motor directly. nr equal to ns minus 1 minus s. Here nr is speed of the induction motor in rpm, ns is the synchronous speed in rpm. rpm means rotation per minute. Always you mind it, ns is nothing but 120 f by p. F is the frequency, p is the number of poles. Here s is the slip. So by using this formula we can understand the speed of the induction motor. Okay. The next topic we will understand stator and rotor parameters. So up to now we discussed about the working of the three-phase induction motor, but we missed a lot of parameters in the induction motor. First we will understand the stator parameters. Parameters means stator consisting of so many elements that have lot of parameters. So generally we can divide into stator and rotor first. If you look at here, generally we are giving supply, electrical supply, AC supply to the stator of three-phase induction motor. To the stator of three-phase induction motor. So this is three-phase supply. This is the stator. Just take it as a stator. Stator generally it will take the supply voltage. So first you have to write the supply voltage. It take the input as supply voltage, take it as V. And supply voltage, it is a three-phase AC supply consisting of the frequency. So you can take it stator frequency. Just assume that it is a stator frequency represents with F. And generally stator is consisting of lot of windings. Stator having lot of windings inside it. We have lot of windings. represents like this. So consisting of the windings means winding is made with the copper generally. Copper is a conductor consisting of the resistance, and it consisting of the AC, that's why it consisting of the reactance also. So we have the stator consisting of the resistance, stator winding resistance or stator resistance. Better to take the winding resistance of stator. Stator winding resistance is R1. Just better to take the R1. Stator frequency, better to take the S. Better to take all parameters related to stator is 1. All parameters related to rotor is 2. And it consisting of the winding reactance of stator. Reactance is X1. Better to take the X1. Whenever the winding consisting of resistance and reactance, the combination of resistance and reactance, stator winding impedance, combination always having the impedance is, take it as Z1. Z1 is nothing but R1 plus JX1. R1 plus JX1. The stator resistance, stator reactance, and this is the Z1. And whenever we are giving the three-phase AC supply to some winding, automatically the EMF is induced. EMF is induced. That EMF is stator induced EMF. Stator induced EMF. That stator induced EMF is represents with the E1. So that E1 equal to 4.44 flux into frequency into number of turns of stator, and we have a factor, that factor is kWs. E1 stator induced EMF, flux per pole in stator, stator frequency, ns number of stator turn. So we will discuss about kWs. So wherever the winding is there, that winding consisting of the factor. This is stator winding factor. Stator winding factor. Okay. So we have to having the stator winding factor. The stator winding factor again divided into, this is Kp and Kd. Kp stator winding, Kds stator winding, like this. So we can represent like this also. So these are the stator parameters. Stator parameters. Okay. Simply stator consisting of the windings. So wherever the winding is there, it's winding consisting of the resistance, and winding, it is a AC supply, it consisting of the reactance. So whenever resistance and reactance is this, automatically the combination equal to R1 plus JX1. Whenever single phase AC supply is given to the winding, automatically EMF induced across this winding, that is represents with E1. So this is the E1, and supply voltage is V, stator frequency is Fs. So these are the stator parameters. Stator parameters. Now we will look into the rotor parameters. Now we will look into the rotor parameters. Rotor parameters. Okay. So rotor is generally, rotor also consisting of the some winding. Rotor also consisting of the some winding. So it consisting of the slats. The slat consisting of the copper winding. So EMF will be induced in these windings. You know that. So when the rotor is stationary or rotor is rotating, EMF will be induced. So rotor, we have to consider the two conditions, standstill condition and running condition. So for that, before that, we will discuss about the rotor reactance, all these things. First, rotor will induce the frequency, rotor frequency is represents with F2, but it's always slip times of stator frequency, not F2, take it as a FR. So rotor frequency always slip times of frequency. So this is depends on the speed. This is depends on the speed. Okay. Next, rotor resistance. Rotor resistance R2. So at running condition, so just take it as before that standstill. If the rotor is standstill condition, it gets some parameters. Standstill condition means rotor is stationary. We have some parameters. Those parameters are rotor resistance is R2, rotor reactance is X2 naught, rotor induced EMF is E2 naught. Rotor doesn't have rotation. That means in this condition rotor speed is 0. Rotor speed is 0. So rotor resistance at standstill condition as well as running condition is both are same. So rotor reactance is represents with at running condition X2. Don't forget it is running condition. The running condition as well as is represented with S into X2 naught. Why it is S into X2 naught? Because generally reactance X equal to 2 phi F. We know that this is 2 phi F L. So if here frequency multiplied with S, automatically X is also multiplied with X. That's why X2 will get S times of X2 naught. Okay, S times of X2 naught. Then automatically it will be changed, right? And we can write rotor induced EMF at running condition. Rotor induced EMF at running condition. Running condition rotor induced EMF represents with E2. E2 will be S into E2 naught. E2 naught means standstill condition. This 0 represents the standstill. There is no rotation, but at running condition E2 will be S into E2 naught. S into E2 naught. Okay, and we will get S at X2 naught for reactance and E2 for like this. So we can write the E2 naught, the equation for E2 naught, that means induced EMF of rotor at standstill, equal, it represents with E2 naught 0 run. E2 naught means at 0 speed, that means standstill. That can be we can written the formula 4.44 into flux into frequency into number of turns of rotor, kWr. This is the rotor turns. kWr means, so better to take not N, better to represents with T. T means turns for phase. So here kWr equal to rotor winding factor. So this is about the rotor parameters. So first important thing, to understand the rotor parameters, first you understand what is standstill condition. Standstill condition is simply nothing but rotor doesn't have any rotation. That means speed equal to 0. So that's why we can write at standstill condition rotor resistance is R2, rotor reactance is X2 naught, and rotor induced EMF is E2 naught. Then the rotor frequency at running condition or standstill condition always S times of stator frequency. And rotor resistance at running condition, there is no change in rotor resistance. Rotor reactance X2 equal to S times of X2 naught. And rotor induced EMF at running condition E2 equal to S times of X2 naught. And rotor induced EMF at standstill condition E2 naught equal generally 4.44 into flux into number of turns into kWr. kWr is nothing but the rotor winding factor. Rotor winding factor. These are the rotor parameters as well as the stator parameters. These are very important whenever we are doing the problems, and when we have to understand the relation between the stator and rotor. If you think the stator and rotor relation is always slip is the relation. Okay, thank you.